I can always just cut stuff out. Okay, well, hello. I am going to do the first lecture for 124 for now, and then I guess we'll go from there. This is the first video I'm recording, by the way. Yeah. First lecture of 124. So, in 124, we are talking about digital circuits. What does digital mean? Digital means that it means basically your like if you're sending a signal from, let's say, your computer to like your headphones or something like that, you would give the data in a set of ones or zeros. So you can have either one or zero or one, and those are your the values that you're working with. Analog is different in that you have a range, so you have from 0 to 1, or it could be 5, or it could be 10 volt, like 0 volt to 10 volt, I mean. So, to give an idea of what that looked like, so, I did not, okay. So let's take a look. So digital means you either have 1 or high, or you may know it as true. True. And then you have 0 or low or false or off. I'm also going to put that, you can refer to this one as on. So digital is a bunch of ones and zeros. So this is what you usually think about when you think about like a computer, for example. You only work in ones or zeros. That is in contrast to analog, which is like your outlet, where you have, a sinusoidal wave, or you have like a triangular wave, or a sawtooth wave, I should say. Because these all are like, they have continuous values. Like if I were to treat this as like a function of, like of y and x here, then this would be your range. And for the range of like something in digital land, that range would exist in a set of just 1, 0, and 1. So the only possible values is 0 or 1. For this one, the range could be any real number or complex number when you start talking about inductors and other things like capacitors. So that's the main idea of digital versus analog circuits. Okay, so what can we do with these values 0 and 1? Well, we can do something called Boolean algebra. It is basically a bunch of like statements and expressions reducing down to 0 and 1. So this is all stuff that you can do on a computer, that you could do on like in any programming language with just true and false. You don't even need like integer or string or whatever like that. You could just use 0 and 1. So let's talk about the binary number system. So we are used to the decimal number system. So decimal, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then once you reach 9, you basically make a hop, and you have 10, 1, 0. So decimal has all these possible values for one digit. I should say that this is only here from 1 to 9, not 10. 10 is a combination of numbers. So these are the possible combinations in decimal. 1 through 9. Now, we call decimal notation base 10, or you could say that it has a radix. Radix of 10. I screwed that one up. Radix of 10. Okay, so base 10, radix of 10 just means when you get up to 10, you go over to the next number. You can see this when you have, let's say, the number, this 124, the course code, right? This is the hundreds place. This is the tens place. And this is the ones place. So each of these is a power of 10, right? So you have 1 times 10 to the power of 2 plus 1 times 10 to the power, not 1. Sorry, that should be 2. 2 times 10 to the power of 1 plus 4 times 10 to the power of 0. If you were to evaluate this, you get 1 times 100 plus 2 times 10 plus 4 times 1 is equal to 100 plus 20 plus 4. Right, so input, output, same thing over here. Right, this is all the base 10 is. This is, you might notice with metric system, when we have powers of 1,000, powers of 10, it actually makes life so much simpler. Because we have, like, it's leveraging this use of base 10. You might know imperial system. I'm sorry, imperial users, but what the heck is 5,280 feet in 1 mile? I don't know. I don't know why this happened, but we're going to move on. Now, binary, as you might be familiar already, is when you have, well, 2 or bi combinations. So if you take a look at, if you were to count in binary, you'd go 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and you would continue. But something to note here is that these are now the only possible combinations. So you don't have what you have here before, where you have 1, 2, 3, 4, 5, 6, 7, 8, 9. You just have 0 and 1. That's all you can see. And with this system, if you're to, we call it base 2. Base 2, or you have a radix of 2. Radix base just means the same thing. Doesn't matter. And now if we were to, let's say, express a number in binary, it would look something like this. If we were to, like, expand it out. Let's say we have the number 1, 0, 1, 1, right? And this would be equal to, 1 times 2 to the 3 plus 0 times 2 to the 2 plus, times 1 times 2 to the 1 plus 1 times 2 to the 0. I don't know, we don't really have a good name for these, but you could say that this one is the ones place, this one is the twos place, this one is the fours place, and this one is the eights place. There aren't very good names for it, but because we don't really use binary in just regular, everyday speech. But what this does mean is that if we were to add these up, as in we would do in decimal, how would that look like? Well, that would look like 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. So we would have 8, we'd have 0, we'd have 2, and we have 1. Add them all up, and we get 11, which is correct. So now this is 11 in, keep in mind, decimal. This is not 11 in binary here. This is 11 in decimal. So that's basically how you convert from binary to decimal. So yeah, so this is going from binary to decimal. Oops. Now, what if you are going from decimal to binary? How do we do that? So let's start with a number. My favorite number, you can't really put it in that's wrong. Let's just pick a random number. Let's say we do 28. Okay, so 28. How do we convert it? What we will do is we're going to divide by, I'm going to kind of lay out the steps. We're going to divide by 2, right? And now when you divide by a number, right, if we have, let's say, 228, so this is your divisor. This is your dividend. And then you have your answer here, which is the quotient. We do care about the quotient. We will go about that, but I want to most focus on this part, the remainder. Now, if you divide by 2, right, there is an operation in programming or math called getting a modulus, or you might call it mod or modulo, and it uses a percent symbol. So let's see, so this operation, let's say you have 3 and you modulo 2. What this means is you get, what's 3 divided by 2? What's its remainder over here? This remainder will be the answer over here. So 3 divided by 2, you have 1, but you have a remainder of 1. So 3 modulo 2 is equal to 1. So you want to add that take that I'm sorry. You want to take that modulus and you want to add it onto your number. Here is where I'm going to just quickly go over some terminology with this, because I didn't quite prepare quite well. I'm going to go over some terminology for binary numbers. If you have a binary number, you can mark something. You can mark it with 2, like here as a 2th base. Here, this we call these bits instead because I'm not exactly sure, but I'm assuming it's because it's in binary, by, bit, something along these lines. This is called the most significant bit. You might have heard of this one. Sorry, this one is the least significant bit. I'm going to finish this up before I go on a little bit of a tangent. You might have heard of significant figures. Significant figures in school. This is slightly related to it. So most significant bit is the most significant because if you change it, that has the biggest effect on the number. If you're to change the least significant bit, it has the smallest amount of change on the number. Like if you were to change 1011 to 0011, then this is the difference between 11 and this is the difference between 3. But if you had to change the least significant bit, this would be the difference between 11 and 10. See, this one is more significant and this one is less significant. So I just wanted to clear that out of the way before I started going, because when we want to convert our stuff to to decimal from binary, decimal to binary, when we basically follow that guide. So divide by 2, right? The first digit you write, like the first digit, or like that you get as an output, first digit from remainder is going to be the most significant byte. Sorry, least significant byte. Sorry. Least significant byte. I should change that. Ooh. And then you keep on dividing by 2, and the last digit is the from your remainder, of course, is your most significant bit. Okay? So if we were to do this algorithm, let's again use 28. So 28 divided by 2 is equal to 14. I should mention that I want to also put the modulo. So 28 modulo 2 is equal to 0. So this part here is our, could I make a different color? It's going to be our least significant bit. Okay, change back to color. So now what do? We're going to repeatedly divide this number over here. Our answer. So we do 14 divided by 2, and we get 7. 14 modulo 2 is going to be, well, we don't have any remainder here, so it's again going to be 0. Then we are going to do 7 divided by 2, and not 3.5, just 3. Think only in terms of integers here. Yes, I'm aware it'll be 7 over 2 or 3.5, but no, don't, oh god. Don't do that. Don't do this. Don't do any fractions or any decimals. We don't want that. 7 modulo 2 will be 1, because we have 3 remainder 1 here. Then we're only going to take 3 and we're going to divide it yet again. So we divide 3 by 2. Again, we have 1. 3 modulo 2 is going to be equal to 1. Then and only then, we're going to again take this, I'm going to put remainder, and bring it back. Now, 1 divided by 2 is equal to 0. So no 1/2 over here. Once we get to 0, this is where you stop. Don't go any further. Can't really go any further, but don't go any further. So we have 0, and that's where we stop. So that will leave us, what we're going to take this 1 that we have here and bring it over. So we get 1 over here. So if you have 3 divided by 2 equals 1, you get the remainder and the actual answer itself. Okay? So if we were to construct this, and just keep in mind that this is the end here is the most significant digit. If you were to construct this, this would be 1, 1, 1, 0, 0. This is in base 2. Now, if we were to take this number and convert it back into decimal, we can try that. So if we were to convert to decimal, it's equal to 1 times 2 to the power of 4. Keep in mind that if you have n digits, then the first number will be 2 to the n minus 1, and then plus 2 to the n minus 2, and you keep on going until you have 2 to the 0, and then you're done. So anyways, you have 1 times 2 to the 4 plus 1 times 2 to the 3 plus 1 times 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0. So these terms we don't care about. But if we were to do this, sorry, I just wanted to put that as a note. If we were to do this, we'd have 1 times 2 to the 4 is 16, plus 1 times 8, plus 1 times 4. You might already see, but if we were to just continue it, we get 16 plus 8 plus 4. 16 plus 8 is 24, plus 4 is 28. And we have our number in decimal. Alright, so that's all about converting between decimal and binary. Why is converting between decimal and binary important? Well, when we use computers, or even just or any digital circuit, or any computer or any digital circuit, we want to use these ones and zeros to represent data, right? We want to represent data. We want it to represent instructions. Now you might have seen stuff like you might have seen stuff like hexadecimal, which is hexadecimal, which is base 16, which you have 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, which is also where hex code comes from. If you ever worked with colors and front end stuff. And I bring this up because you might have seen assembly instructions, or if you ever take a look at disassembly when you're compiling a program, you might have seen in hexadecimal here. Hexadecimal is just a really compact way of writing our binary. So if we wanted, hexadecimal is just like a translation layer for raw binary. We interpret everything in binary here. We use it for data, for instructions. It's really important for, let's say, AND gates, NOT gates, OR gates, and how they interact with transistors and read-only memory, or ROM, even RAM, and etc. Right? So having a good way of translating between actual numbers that we humans can understand and numbers that computers can understand is a really powerful tool to just reduce everything down to binary, so we can actually do stuff like AND, NOT, or with it. And that's the big spiel about it. Now, let's continue on to lecture 2 for 124, which is binary logic. So as we have seen, as I said previously, binary, we want binary because you can do stuff like binary logic. Now I have already kind of introduced between the 0 and 1. Now this one can be low, off, false, open, and like there's a lot of stuff you can say about that. Where this one is high, on, true, closed, and etc. You can represent it like this. You have, I'm gonna go like a thicker one. Let's say you have a gate, right? If you were to have an open gate, there is no voltage going through, and you have 0. If you have, let's say, a gate and it's closed, this would be 1, right? That's basically everything there is to 0 and 1 and binary stuff. Except it isn't, because there is stuff that we can use logically. So we're going to put it in more in a mathematical sense. So I'm going to talk to you about something called binary variables. And these are variables that exist in the set 0 and 1. So basically, if you have x and you have y, they can either be 0 or they could be 1. Now, the thing is, we can have them independent of each other. We can have x being 1 or it being 0. We can have y being 0 for both of x being that, or we can have y being 1 for both of these x inputs. And this is where the concept of a truth table naturally takes course. If we want to compare, let's say, if we have a function and we have x and y as inputs, then we want to define what those outputs could be for all our possible inputs. It doesn't make sense to just for a few of them. So we define some logic operators that you might be familiar with, that you might not be familiar with. Well, we're still going to go over it anyway, so logic operators. We have 3 key logic operators. So first we have and, right? We have not, or, and then we have not. Now, so this is the like the operator, and this one here is like should I do symbol? Yeah, sure. Symbol. Right. And with and, we have a symbol of, let's say, multiplication, or it could be nothing. I'll explain what I mean by nothing over here. For or, we have plus, or logical plus. We call this logical multiplication, logical addition. And we have not, we have prime, or you have overbar. So let's do some examples. So if we have x and y and they exist in the set 0, 1, then we have the logical and, or like the logical multiplication of them would be x multiplied by y, or x, y, just like that. That's what I mean by nothing here. For or, we have x plus y. And then for not, we have x prime, you have x bar. These ones and these ones, it doesn't really matter, and you'll see me constantly switching between them. Just keep in mind that they mean the same thing. There's nothing really different about them. There's nothing special about using any of them. we use parentheses to enforce order. So if you have parentheses, hold on, it's bothering me. Parentheses, and these are just used to enforce order. So if you have parentheses, they are going to be evaluated first, as with any BEDMAS operation. So if you were to do x, y like this, this would be done first, and then this would be done second. Now this order is also going to lead me to the next point, which is what is the order of binary logic. You can remember it as P now. P now, I don't know. P now, where P stands for parentheses, N stands for not, and an or. So first you do not, then you do and, then you do or. So this expression over here is not equal to this expression over here. And I say that because you would have you have different orderings here. So first x or y and x. Actually, no. I messed up because this is absorption. This is something called absorption, which I think does work. So we're going to just define z. These are different. Here we have x or y, and that result is ANDed with z. Whereas here we have y and z, and that's ORed with x. So it's going to be different here. This one is going to be first, and then this one's going to be second. I'm just saying that the order is different. The results might be the same. I'm not going to go ahead and check, but just keep in mind that's the order for logic operators. Now, you might be familiar or not with logic gates for it, and logic gates are the physical implementation of these mathematical logical operations. So the logic gates is a physical, or well, as close to physical as you can get, physical implementation of our logical operators. Okay, so that's all it is, the physical implementation of our logical operators. Our logical operators need not be physical, but we can definitely find a physical implementation. So an example might be like a flip-flop, but that's going to be later. That's going to be later, not now, but you'll definitely see it later. So we define these logic gates and logical operators in terms of truth tables, and truth tables are kind of saying, if I give you some possible inputs or outputs, what will the result be? Now, we're going to kind of start steering away from truth tables, but it's going to kind of show you some of, it will help me kind of describe the nature of and or. So let's start first with the AND gate. Oh god. AND gate. Right? Oh, I am going to fix that. You can't even read that. I can't even read it. There we go. So AND gate. How does this look like? It has this symbol. So it looks like you have a line. You have one output. This is going to be called F. And you have two inputs. I'm going to call it x0 and x1, respectively. And if we were to make a truth table, so I'm going to separate the output on the right side. I'm going to separate the inputs I kind of go over why truth tables kind of are like sucky and why we want to go away from them as soon as possible, but we'll entertain it. So in this case, f is a function of x0 and x1 here, and our AND gate is going to be the logical multiplication of each. By the way, the order doesn't matter here. I'll talk about that in a bit, but the order doesn't matter here. So what does the logical AND mean? So logical AND requires that both inputs are like all inputs, I should say. All inputs, because you can have multiple inputs. All inputs are true or on. So if you have x0 is equal to 0, this one's 0, then nothing is on. It doesn't work. It won't go through. If we have 0, 1, again, same thing, 0. Both of them are not on. One of them's off. If we have 1, 0, again, same deal. We have one on, but we don't have the other. However, if you have 1 and 1, then it turns on. This is the logical AND. Now, you can, AND gate just requires that all the inputs are on, so you can have an AND gate that looks like this, where you have like x1, x2, all the way to xn. So x0, x1, all the way to xn, and you have f of all those variables. You can have that. Like that's definitely something that you can do. It's just like a little bit bulkier, and it kind of better for you to have like a simple explanation first. That's all about the AND gate. So all inputs are on, and that will give you the output is on. Now, let's talk about the OR gate. OR gate looks like similar. Oh gosh, I wanted to show you how these look, but I can't even really draw them. Okay, this one's x0, this one's x1, this is f. So again, two inputs for now. This is again going to be a function of two variables, and it's going to be x0 plus x1, a logical addition. So if I were to make a truth table, I'll just quickly, oh, that looks wonky. Here, maybe like that, maybe like that. Just trying to go fast. x0, we have x1, and we have f. So the OR gate requires, in order to turn on, requires that at least one input is on or true. So all it requires. It's like the most like the most unbothered gate. Just needs one. All it needs. So if we have 0 and 0, none of them are on, so we just have 0. If we have 1, 0, then at least one of them's on, which is x0, and we get 1. 0, 1, 1, 1, 1, 1, right? And that's everything about the OR gate. You can see how the AND gate kind of contrasts. There's these middle two inputs that are 0. The OR gate has them on. AND gate has them off. Of course, as with the AND gate, you can have any number of inputs. So you could have x0, x1, and then however many you want to xn, and then f. Same thing. At least if at least one of these is on, then the functions on are true. The next and last gate we will talk about for now is called the NOT gate. Now it has this symbol. Only has one input. Has a circle here and then continues here. So this one is x0. This one's f. Now keep in mind that this dot, this circle here is the actual like not portion. It inverts or inverts the input. If you have a symbol like, if you have, you know, this and like that, this is just called a buffer. And I'll actually go over both of them here because we can. For the NOT gate, again, remember it takes only one input. It will return the inverse of the signal coming in. So if you have f, you 0, 1, you have 1, 0. And that's basically it. You can't have really multiple inputs in it. You could probably have a bunch of them like in parallel. But you can't have, you know, multiple inputs. It just doesn't work. However, the buffer is kind of similar to the inverter, but instead of you know, just being instead of inverting, it just passes through the same input. You might be wondering what's the point of a buffer if it just returns 0 and 1. Keep in mind that these logic gates are implemented with transistors. So you might have seen this symbol. So a transistor, right? So a transistor goes from collector to emitter, and there's a gate. You can take a look more into transistors. I don't think we'll be covering them this term, but they are very fascinating. But each one of these are implemented with transistors / diodes. In that case, I just want to say then that why we would have a buffer. Well, with a transistor and with a diode, you might have seen it, you can't actually go in the opposite direction. You kind of can with diodes, but like that's more of a linear circuits problem than a digital circuits problem. It just makes sure that the input can't go back. So the x1 f, the input can't go this way. It can go this way, but it just can't go the opposite direction. Same with the inverted one. Can go forwards, can't go backwards. And that's basically everything. I'm just going to write this out for completeness. Inverts the input, and this one returns the same input. Okay. Otherwise, that is everything for our logical operators. Now, there are different. I did show you like two ways of representing our Boolean, our logic functions. So we have schematic. No, we didn't go over schematic. Sorry, we went over algebraic. So that's where we have f of x1, x0, x1, and x2 is equal to, let's say, I don't know, x1 and x2, and that's all ended with x0. So this is algebraic notation. There's also the truth table notation. I'm not going to copy the example from class, but because it's really long. But the truth table, yeah, you just basically make a list of inputs, and then you have an output, and then you just put all your possible combinations. Now, I was saying before that I wanted to tell you why truth tables suck. So I'm gonna go a little bit of a spiel why truth tables suck, and then we'll go on to the third type. So why do they suck? Because when we have algebraic, right, we can like choose any of our inputs, and we can see what the output would be. With a truth table, we have all the possible inputs, which means that we have to list if we have 0 1 0 1 0 0 1 1 0 0, like, and then again you have to do the same thing but for all the ones, and it's a lot of inputs. In fact, it's more specifically 2n number of possible combinations, right? So where if you have let's say your n, or your number of inputs, is equal to 2 here, right? Then you have 4 combinations. 2 to the power of 2 equals 4. But if you have 3, then you have 2 to the power of 3, which is equal to 8 possible combinations. It just doesn't scale. Like if you're to do like a logic function with, I don't know, maybe even 6 or 7, 2 to the power of 6 is already at 64 inputs, 64 combinations. In 7, 128, and it keeps on going further. So truth tables get more and more inefficient the more inputs you add. So truth tables kind of suck in this regard, which is why, like, later on you're not going to see too many more truth tables. And so that's why truth tables suck. The last representation is called schematic. So this is actually using our logic gates instead. So let's say we have this function over here, right? We have x1 and x2 anded by, x1 or x2 anded by x0. So how would that look like? So first we'd have x1 and x2. These would be ORed, not ANDed. So it'd be ORed. And then we have x0. And then these two inputs here are ANDed together. And we have our function. This is schematic. Yeah, it gives us like a way. This is closer to the real implementation. Okay, so that's those are the 3 different kinds. You have algebraic, truth table, and schematic. Now, this 1 and 0 stuff is something called Boolean algebra. And it was kind of discovered / invented by a guy named G. Boole. We only care about the last name. We don't really care about the first name. So he came up with 6 postulates for Boolean algebra. Now, there is so much about this, so I'm going to try to get through it as quick as possible here, because there is a lot. So, let's talk about the postulates. Postulates of Boolean algebra. Okay, so postulates of Boolean algebra. First is that we have closure in set B. Sorry, I should have defined what set B is. Set B just is set that's equal to 0, 1. So it's just, so this first postulate is just saying that no matter like what operation we do, and no matter what operation we do in set B, we can never like get out of it. Like we can't get 2, for example, because 2 isn't in the set of B. I'll just say venture out of B. Right, so you can't go out in if you have to. So you have closure. Second one is that you have identity. So you might remember, if you've taken linear algebra, they have something called the identity matrix. Why is it called the identity matrix? If you were to multiply the identity matrix as any other matrix, you just get that same matrix. So if you have like A multiplied with I, for example, you get A, right? Just the identity. The same thing happens in Boolean algebra. So I'm just gonna, my computer's not liking it. Doesn't want to move it. So we have an identity element. So let's say if that's 2 of these. So if you were to logically AND x and 1, you just get x, right? So if you do like a truth table, if you had 0 and 1, you just get 0, right? Same thing. You get 1 and 1, you just get 1, right? So that's the identity. The second one is if you OR anything by 0, you just get the same thing as well. So if we OR 0 and 1, we get 1. As I say, no. 0 x 0. So 0 and 0 will give you 0, and 1 and 0 will give you 1. Right. So these are identity. It gives you the same input, the same output for the same input. Okay, that's everything. I remember how I said for the AND gate that doesn't matter which order I do. Well, there's this postulate. It's called commutative. Oh my gosh. Commutative postulate. So commutative just means that it doesn't matter what order you do anything. So if you AND x and y, it's the same thing as ANDing y and x. And if you OR x and y, the same thing as ORing y and x. Order doesn't matter here. Now there is the fourth postulate is distributive property. And this one is kind of tricky. So it basically says, okay, if you have x, I should just mention that I didn't mention it, but hopefully set it here, that x, y, and z all exist in B. Not doing anything different. Should have mentioned that first. But if let's say you're ANDing that you OR y and z, and then you AND it with x, then you can this will be the same thing as x and y or x and z. So just to kind of give some order here. You can kind of think about it like expanding. And so like foiling stuff. So x and y, right, for this first one here. And then you have this and x and z. And then you can factor this. You see that there's x in both of them. So you have x multiplied by y plus z. Okay, so that's a kind of a distributive property. You can either, this is kind of FOIL. It's not exactly FOIL, and then you can also factor. That's kind of like an easier way to think of this operation. You can go through the truth table to see why this is true. In fact, I'd kind of encourage it, but I'm not going to go over it right now. Should I? You could try for some possible, and we could try some possible inputs. Let's try. Okay, let's say we have. Let's try this. Let's say we have x or y plus z. So let's say we have zeros for both y and z, and we have 1 for x. And then we'll do the same thing for here. X and y plus x and x. Sorry, or I keep on saying plus, or x and z. So x here is 1, y and z here are both 0, so this statement becomes 0, this statement becomes 0, and you get 0. This one you have 0 and 0, and that just becomes 0. Right, you could try any possible combination. If y instead here was 1, we could do x and y plus z. Actually, I'll just substitute in the numbers directly. Don't need to. Oh, it's erasing stuff. 1 and 1 or 0. We get 1 and 1 equals 1. And if we do the same thing over here, you could do, let's say, 1 and 1 and 1 and 0. You can kind of see, like, if any of these ones in the bracket are true, then it just depends on the result of ANDing x, y. It's the same thing as splitting x and y for x and z. Hopefully that's like kind of a little bit more obvious here, but you will still always get the same result. You could try for every input. You can start a truth table. The columns would look like x, y, z, and then you could do y and z. Let's say y or z, and then you could do x and y or z, right? And then you could try. you could continue on this, and then you have your final expression over here. You have x and y, x and z, and then you have x and y or x and x and z. And you can construct that truth table. It will take like 8 inputs, but you can do that if you would like to. However, I'm not going to do that because I don't want to focus on computations. I kind of want to focus on theory here. That is postulate 4, distributive. There are 2 more postulates. So the 5th postulate is something called like additive inverse. It's the same thing as you might have heard this in linear algebra. Same deal. So if you have A and you AND it with A naught, then you always have 1. So if A is equal to 0, then and not A naught is, and not A is going to be 1, so it's going to be 1. If A is equal to 1, A naught is going to be equal to 0, so it's going to be equal to 1. Right. So this is the first one. First one, and then the second one is let's see, A and A naught is always going to be 0. So if you have if you have 0, then its logical inverse is going to be 1, which is going to be 0. If you do 1, its logical inverse is going to be 0, and it's going to be 0 again. So that's just another thing, additive inverse. It's kind of weirder in here because usually in linear algebra, if you or like just any sort of algebra, if you add, let's say 5 and you add its inverse, -5, let's say negative thing, it'll be 0, right? Even for vectors, you get 0 vector. But for here, it depends on which operation you're doing. Now, sixth and last one. So it basically says there exists two elements, A, B, which exists in our set of 0 or 1, such that, or where, A is not equal to B. So this is a saying that they are distinct. You don't need to, you can use any value for A and any value for B, as long as they're 0 or 1, and it will hold. Alright, that's all the postulates. There is a long list of properties. I will probably just copy them out. Absorption. I'll go a little bit. I'll go over absorption. Let's talk about them. So, let's talk about them. Yeah. So some properties. So first is an always true property. So from before, if you add anything with 0, it will always equal 0. Sorry. Yeah, if you add anything with 0, it always equals 0. And for B, if you add anything with 1, it'll always be B1. These are always true. 2 are identity ones. So as I said before, if you add anything with 1, you always get x. And if you add anything or anything with 0, you always get x by itself. Now there are 2 more. If you add anything by itself, you get itself. This is true. 0 and 0 will always equal 0. 1 and 1 will always equal 1. You can't have any different because we're assuming x is the same here for each of them. Last one is x, and x is always equal to x. So 0 and 0 is equal to 0. 0 or 0 is equal to 0. 1 or 1 is equal to 1. That's everything. So these ones are the identity. And this one is always true. Okay, so now let's go on to the next one. 3. So again, this is with the additive inverse. So x or x bar is equal to 0, and x or x bar is equal to 1. Bar, again, same thing as the prime. It doesn't matter. It's just the same thing. 4. This is a double negation probably, so it's actually just not one. So if you were to take, let's say you have x and then you not it, and then you not it again, you always get x. Right? So x not, not. Right? If you were to do that, 0, 1, 0, 1, 0 is 1. Right? This is always true. 5 is a commutative property, which we discussed about. So yeah, x or y is equal to y or x. And again, x and y is equal to y and x. Doesn't matter. Again, the order doesn't matter. It's quite cool. It also doesn't matter what way we group things. So if we have, let's say, x and y and z, the same thing as x and y and z. Same thing happens for for or. X or y or z is equal to x or y or z. Pretty standard. So this one is, sorry, I can't write. Okay. And I did go over one of the distributive properties. There are actually two of the distributive properties. So I'll just put the one that we did up above. So that's one of them. The other is if you have or on the inside now. So if you have this now, then you just have x or y and x or or not and z. Okay, so that's everything for that. For this one, actually, you don't need the parentheses because and is operated before or. But if you want, I just put them there just in case you want to kind of see the order that you do things. So this is distributive. Now there is a special one called De Morgan's law. Basically it just says this. So if you have x and y, and you were to take the naught of this, it would be equal to x naught or y naught. So basically, let's say okay, I have I want to search something. So I want to search, okay, I have some documents, and I'll actually write it here. I have documents about dogs, right? We have dogs, we have cats, we have something about dogs and cats, so you have dogs and cats in here, and then you just have something that has like neither, so it's just like, let's say about I don't know, trains. All right, let's say I wanted to find let's say, okay, I want to find not dogs and cats. So what is this? So what would this mean? So it means, okay, if so dogs and cats, the only one that would be true here would be, oh my goodness, oops, would be dogs and cats. So we want anything that doesn't have both dogs and cats. So this would be dogs, cats, and trains. Right? Because dogs doesn't contain cats, cats doesn't contain dogs, and trains doesn't contain anything. Right? If we were to rewrite this in the other way here, so if we have not dogs or not cats. So or is really important here, because if we let's say, okay, not dogs, so dogs, so this one has dogs, but it doesn't have cats, so this one is actually valid as well. Cats here, it has cats, but it doesn't have dogs, so it's also valid. Dogs and cats, well, both are out for the count because we have dogs and we have cats, so we can't choose from either of them, because then not dogs, it'd be this one has 1, this one has 1, the not makes it 0, and then we or 0 and 0, and we get 0. So this one is out for the count, but the other ones are not. And then specifically for trains, well, it doesn't have dogs and it doesn't have cats as well. So it doesn't have not dogs, not cats, it's also valid. So that's more so of De Morgan's law. There is a second thing as well. So that's for this first case. Then we have a second case where we have x or y not is equal to x not and y not. So you'll notice here that if you want to like take anything like this, if you want to go from this one to say from this first part to this second part over here, then you would have, let's say, you would so you split this not and flip this operation. So for this one you have and, you flip it to or. For this one you have or, you flip it to and both of them have just same thing. Let's go over the same example for the second one. So with this one is not dogs or cats. So let's kind of go over which ones that would be. So dogs so this one here has dogs. So it would make this one true, it's inside, but it has this not. So this one is out for the count. Cats, it would make this one true, so this whole expression true, but with a not, it's out for the count. For dogs and cats, again, both of them are true, so they are out for the count. For trains, though, we have no dogs, no cats, so and we inverted, so this one gets us something that's true. I will give kind of a red here and a blue for these examples, just so that when you like take a look at it, you can do that. And then if we were to do not dogs and not cats, then we would have, well, we can go again case by case analysis here. So not dogs, so dogs is here. So if we had, so dogs is 1 becomes 0. Regardless of what we have for cats, it's going to be 0. So it's going to be false. Okay, so this one's true, this one's false, and whenever you and anything with 0, it's always going to be 0. So no dogs. For cats, again, same thing. Cats is true, not cats makes it 0. Anything added with 0 makes it false. So no cats. Dogs and cats. If we have if we have dogs and we have cats, then we have 0. Let's say we have 1 and 1. Then the not makes them both 0. So 0 here, 0 here, 0 and 0, 0. Right, not going to work. However, for trains, we have dogs is 0, cats is 0. So cats, dogs, not dogs would be 1, and not cats would be 1 as well. And that's basically everything about De Morgan's law. There is one more special property, and that is called absorption. Don't worry, this is the last one. We're going to be done for this one. So absorption basically says, okay, if you have, let's say you have x and or x and y, this is the same thing as x. Same b is just going to be the same thing but flipped. Okay, so this is how can I don't want to use truth tables for this because it's kind of truth tables. So I'm going to show you how you can actually prove that this side is equal to this side. So let's start. X or x and y is equal to x, right? If we were to factor out an x here, we can do that. So if we take a look at distributive property, it should be this one over here. You can see, okay, if we have x and x plus z, like I like kind of show you. Okay, sorry. So absorption, we have x or x and y equals x. If we are to factor out x here, which we can do x1 and 1 and or 1 and y. Sorry, I mean that this is here. And if you were to do this in reverse, you know, you could distribute it. So it'd be x or x and 1, or x and y and 1. X and 1 will always, by our identity rule, will always be x, and anything ended by 1 again is going to be the same thing, so we just resolve with the same thing. So that leaves us with x 1 and 1, or 1 and y. Now that leaves us, we can see that's equivalent to x and 1 or y. Because again, identity here, anything ended with 1 will just be itself. Then we can see, okay, if we have 1 or y. If y is either 1 or 0, it actually doesn't matter. We have the same deal over here. So it's going to be the same result. It's going to just be 1. So you have x and 1, and anything ended with 1 is just going to be itself, so it's x. You can also, I don't know if I'd leave it as an exercise for you to do, but you can try the same thing for the second property over here. I'll leave that one for you to do as practice. Otherwise, that is everything for the properties of Boolean algebra. Alright, so let's talk about synthesis. Recall, so last time I talked about algebraic notation, I talked about schematic notation, I talked about truth table, right? So actually I'm going to move these a bit apart. So let's say you're doing your stuff, and you have an algebraic model of a function. To go between algebra, and you want to convert it to a schematic, so that direction is easy peasy. It's easy peasy. You can go from an algebraic model to a schematic model pretty much like instantly. It doesn't take much effort. The same is true for the converse. If you want to go from schematic and you want to find out its algebraic model, it's also fairly easy. Now, truth tables. Truth tables. If we want to go from an algebraic model to a truth table, this is easy. However, because you can put all of your inputs in, do your stuff, and then you got a truth table. However, this going from a truth table to an algebraic or a truth table to schematic is to be determined. It's not really easy. We do have ways to make it easier, but it's not as easy as going from algebraic to schematic and all the other easy routes. So that's kind of like the basis of synthesis. Now I'm going to also talk about another important thing here, which is cost. I think I should probably go to a new thing. Cost basically means like the number of operations to do. Number of operations. Right. We define it to be number of operations as well as the number of inputs. So if you're building a circuit, right, and let's say you want to you're building a circuit and you want to, let's say, you want to construct it using real world implementation stuff, you need to go out and buy physical components to do that. And you need to build like a bunch of sorry, I got interrupted. And you want let's say, okay, you want to build up a circuit and you want to go out and purchase physical components to do your operations. This costs money, right? You can't just go ahead and get free AND gates from like 74HC series. Like, it's not free. And the number of inputs also determines the cost, because those 74HC like components, they only have like 8 inputs, and if you need more than that, well, that's going to cost more. So we define cost to be the number of operations plus the number of inputs. Now, there is an important no. Any inputs that are true inputs. So I don't mean that they're any like fake inputs. I mean that like any inputs which have an initial value of true and complements. So let's say not. So let's say if you have if you have x and you have not x, then these two are free. These two are free. Free real estate. So if you have this x here, this one will cost something, but this one will be free. I don't know exactly why you have to pay to get a NOT gates, but for this quest, you consider them to be free. So of all the product terms, so in order to do this kind of thing, I will introduce I'll introduce something called min terms and max terms. So min terms are basically min terms are product terms, I mean logical product terms, in which each input variable occurs. So you have to have all of your inputs in the product term. So an example, so if you have f of x1, x2, and x3, a min term would be equal to the product of all of them. So x1, x2, you could have x2, not x3. This is a min term. Min term. And that, however, if you have something like x1, not x2, this is not a min term of f. So this is a min term of f. This is not a min term. Right? So min term, something important to actually we'll go over that. Right? So that's what a min term is. You also have something called a max term. So a max term is an sum term. Sorry, forgot the word for a second. Sum term, in which again each input occurs. So you can't have no inputs. You can't have one input that's just not there. You have to have all of them. Sorry, I have like a mouse draggy thing on my pen, so I'm accidentally clicking it. I'm accidentally dragging it. Okay, so fx1, fx2, and x3. So x1 or x2 not and x3, this is a max term of f, right? This is all good. If we have x1 and x1 or x2, this is not a max term. That's basically everything for that. So let's say you have, I'm gonna make a truth table. So I'm going to make a huge truth table here, just because I kind of want copying an example, but I also want to I also want to kind of give like an idea of how you construct these min terms and how you construct these max terms. Because for your min term, you want your min term to be 1, and you want your max term to be 0. I'm going to, yeah, we can do that. We can do that. I actually constructed it bigger than I needed it to be, but who's counting? So, let's say you have x1, you have x2, and you have x3. So a min term, there is a special symbol for it, which is m, and you have max term. Its symbol is big M. So if you let's go through the variables again. Truth tables suck, but we are using it because I don't want to explain this all by words, and you probably don't want me to explain it all by words. It'd be so boring. So for min term, we want to force this min term to be 1. So you kind of take a look at something special, right? For a product term, right? If all of them are 1, then this min term will be 1. For a max term, though, we want all of them to be 0, because if one of these is 1, that's like, who cares? Who cares about OR gates equaling 1? We want them to equal 0. Right? You can actually go back to all the way back to our AND and OR and NOT gates. Because our AND gate, there's only one possible input here, where you have an output of 1. For OR gate, there's only one input where it's a 0. And this is very important, because then that means we can it'll help us go from our truth table to an algebraic or a schematic representation. So min term, we start at m0 and we just go from there. So we want to have we want to force this min term to be a 1. So to do that, if we have any zeros, we want to not them. x2, not. x3, not. You can also use the prime notation. Again, whatever floats your boat. Doesn't matter. But I'm going to speed up the process. I'm going to edit them so you can see, because these are not all correct. Don't worry. So for m0, I need to change these two. We're going to put m1, 2, 3, 4, 5, 6, 7. So for m1, this one is already 1, so we want that to be 0. We don't want to negate it, otherwise our min term is going to be 0. However, these ones we want to negate, because then it will make these both 1s, and then we'll get there. So we'll just go and remove the bars from any of the variables where they have where the inputs have 1. And we don't want to remove the input. Here, here, and all of these here have theirs removed. So you notice if I were to go ahead and take all of the take all of the if we were to like put these inputs into the associated minterms, we would always have an input output of 1 for its associated minterm. Though if I were to put 1 1 0 0 into this one here, it would be 0. Max term, so again, 1, I'm just gonna go, it goes 1 plus x2 plus x3, and then we'll just copy it, because I don't know if we all like would like it if I were to just draw everything. This is where I will give a shameless plug to, not a plug though, I'm just doing this just for the heck of it, but if you were to do, if this program here is Obsidian, and this is a plugin called Algebra, which is so helpful. Oh my word. Oh, alright. So, let's go over it. So for our max terms, we want this to be equal to 0, because if any of the inputs are 1, who cares? So if it's 0 here, so we're going to take the inverse of anything where any of the variables where its associated input is 1. So here, 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 and finally at the end, all 3 of them are done. Okay, so why are these min terms important, right? So for any for any particular input pattern, right, you could choose 1 0 0. For any particular input pattern, its associated min term is equal to 0. So it equals, other way around, equals 1, right? All others, so all other midterms for that input pattern my computer is not liking how much memory I'm using. After all other minterms for that input pattern are 0. All right, so I kind of went over that before. However, for any pattern as well, just going to same deal. Its max term, its associated max term, is 0. And all other max terms are 1. So you notice for any input, its min term is 0 and its max term is 1. And for any other min terms, if it's not of the if we have a mismatch between the input pattern and its min term, then its max term will also be will be the inverse of the min term, and the min term will be the inverse of the max term. So in general, mi, so the min term bar, is equal to max term I. For I equals 0, 1, all the way to 2n minus 1. Okay, so that's basically everything for it. Okay, so if we are given there are two ways to construct a function from a truth table. So there are two ways. So the first way is something called canonical sum of products. The second one is canonical. Do you want to take a wild guess? It's going to be product of sums. This one's called SOP. This one's called POS. I'm not I'm not saying that anybody's POS. I mean, so okay, so let's first go over this method. So canonical SOP. So let's say you have a truth table, right? And you have a result that's equal to 1. In that case, remember that our min term for any particular input pattern will equal 1. So we want to take the input. If we take that input of that min term pattern and we take any logical ORs, then we can kind of force our function to be true whenever one of those min terms is equal to 1, right? So let's say, I'll just do like a kind of quick example. If we do, let's say, for like a input function, we have that this input is 1, this input is 1, and this input is 1. What we do is we take these min terms here and take and OR them together. With those, if we take those ORs, remember that our min terms only will be 1 when that particular for that particular input pattern. So we have 1, 1, 1, and if any one of these patterns is true, then we have then we get back, it will find like a pattern. We find pattern to kind of force it to be like a function. It's kind of like it feels kind of hacky, if I say so myself. So let's do, I'm just going to erase this and just going to go to like a real example. So let's say we have, I don't want it to be black. Let's say we have a truth table. I'm going to use 3 inputs here, but I hope like this should be enough to like kind of get my point across what canonical sum of products is. Please note that for canonical sum of products, you can simplify it to be a lower cost because it's not necessarily the lowest cost, but it won't be a canonical sum of products anymore. Canonical sum of products refers strictly to the logical OR of all the min terms. So let's make an example. Right, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Okay, and let's say we have this input is 1, this input is 1, this one is 1, and this one's 1. Okay, so we will construct some min terms out of these. So for this one, we have x1, x2, x3, and these ones will be barred, because then this one will be forced to equal 1. Do the same thing here. We'll do x1 bar, x2, x3, that's equal to 1. Then we take that min term, so x1, x2 bar, x3 bar equals 1, and then last one here is x1, x2, x3 plus 1. Keep in mind that we will keep these names here. So this one's M1, this one's M4, M5, and this one's M7. Right? So canonical sum of products, I can write it as a function. So f x1, x2, x3. We go to M1 and M4, sorry, or M4, or M5, or M7. Okay? We can write this as a sum of M1, M4, M5, M7. Okay, so we can write it as kind of that, you know, particular arrangement. So I will do some, so this here, this strictly here is the canonical sum of products. So if you simplified, it won't be canonical, like it won't be the canonical sum of products, but we can get actually a lower cost out of it and lower complexity. And besides, who wants to go all through this? So take and then we can do some algebraic manipulation over here. So we can, let's see what we can do. Okay, so what you can do is we can take a look at this. We can see, okay, x1 here is common between both these terms. I'm actually here and here is equal to x1. Yeah, so it's we're going to factor out x not x1 and x3, and then we can use x2 and not x2 or x2, and then we OR it with this one. We're going to factor out an x1. You have an x bar 2 sorry, I'm just bar x3 I'm actually not sure if we can simplify that one over there. I actually need to do more practice on that. But this one will cancel out to be 1, and anything ended with 1 will just be itself. So you can think it's and 1, and this, it just goes away. It just doesn't appear there. I'm sorry, thinking for this one. x2. No, I don't think you can, because remember, we can actually do de Moivre's here. And sorry, I actually need to check one thing here. If we do I just need to know. I think we can combine them into one term. Sorry. 1 second. I'm going to figure this out. I did a bit of truth tabling, and it appears we can't actually simplify that. So, yeah. That's great. Anyways. This is all just to say that I have, like, you can see that I've simplified this here. Like, this is sort of simplified. But keep in mind, it is not the canonical SOP. So keep that in mind whenever you're simplifying it. It's not going to be canonical. This is the canonical here, over here. This is, but this is not. The second method here is POS, so canonical product of sums, and it's about as much as you expect. So I'm not going to go over an in-depth example. You can try to do it again. I'm just going to, although I'm kind of, no, I'm going to go a little bit of an example, but I'm not going to go fully. So I'm just going to copy this over, right? And now we want to find where these inputs are 0. Because remember, when we want our max terms, we want to force our max terms to be 0. Because that's the only, forcing them to be 0 means that all of the terms inside are 0. Again, keep in note, if we go all the way back to the OR gate, right? This is the only input that's this is the only part here where it's 0 for the OR gate, where all inputs are 0. So it's kind of special when OR gate is equal to 0, because that means all the inputs are equal to 0, and we can use this for our max terms. So we'll do the max term here. So we'll do x1 and x2 and x3, and then we will do x1 or not x2 or x3. So we'll do not x1 or not x2 or not x3, and then we will again do x1 or not x1, not or not x2 or x3. So for canonical product of sums, it sounds about like you expect. So it's going to be equal to f of x1, x2, x3 is equal to m1, this is going to be m0, m3, m5, and m6. Right? So you can represent this as, this is pi, by the way. It's also used for, you might have seen sigma for summing, but this is pi for multiplication. M0, M3, M5, M6. Then you can just take these ones over here, and you can go ahead and go wild with these over here. These are x1, x2, x3. You can go wild with it, and put it in as a product and simplify it if you so desire. You can go expand and simplify using your distributive property, and then you can simplify it. I'm not going to go over all that work though, because you could do it on your own time. I just wanted to show you what canonical product of sums and canonical sums of products are. Keep in mind, I didn't explicitly say it, but like a logic function can always be expressed as canonical sum of products or canonical product of sums. And when I mean always, it can always happen. As I just showed with that example, we can do it for any function. It doesn't matter which of these are 1, which of these is 0. It can happen for anything. And that's really powerful when you need to, when you have a truth table and you want to make a physical implementation. You do this, and you can choose the logic gates that will get you that desired output. However, that is everything for 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 Boolean logic and digital circuits for the first week. Yeah, this is all just first week, 2 hours of content. And I will do this now again in a week from now. Okay, bye bye.